Welcome. In this lecture we start a new chapter that deals with model selection, linear model selection and regularization. The idea is to have methods that make linear models more effective. Now, we already know how a linear model works. It is just, as you can see, a linear combination of the predictors through the coefficients beta 1 to beta p, if we have p predictors. There is also an intercept, beta 0, and then we have the irreducible error. And the idea is to have techniques that extend this model in such a way that it can deal with situations in which, for instance, you have many predictors, not so many data, and so you need techniques to simplify the model and avoid overparameterization and overfitting. Further extensions will be dealt with in chapter 7, in the next chapter, and there we will start accommodating non-linear but still additive relationships. Then we will move further to non-linear models in the subsequent chapter. Okay, now why linear models? Well, I should stress again that linear models are simple, that real world as a rule is not linear, of course, so linear models are an approximation, but they have some definite advantages. One of these, perhaps also the main one, is the ease of interpretation. So if you have a linear model, it is quite easy to interpret the role of the predictors, and in addition, it must be said that even if approximate, in many situations, they also offer good predictive performances. Okay, and so now the issue in this lecture is introducing some ways to improve the linear model, because so far we have been concerned with the use of ordinary least squares in order to estimate the coefficients of the linear model. So the question is, are there alternative ways to obtain linear models that are even more effective? Okay, and what are the reasons behind our search for these alternatives? Well, there are two main reasons, and they are very closely connected to the advantages of linear models. So we want to preserve as much as possible the good properties of linear models also in difficult settings. And a first issue is the one of prediction accuracy, and we know that the linear model can perform well, but it's going to break down when you do not have enough data, and in particular it may happen that the number of predictors is even greater than the number of data, and this means that you will not be able to estimate the predictors because you will have a number of unknowns which is greater than the number of equations. And even if you have enough data but the number of predictors is very large, their variance is going to be quite large, and this means that the model can be quite unreliable, and this is what we call overfitting. In other words, I also use the expression that the model learns the noise. Since you have too many parameters, too many degrees of freedom, some of them are used to learn unessential features in your training data. And this is not a good thing, because when you will apply your model to predict to make predictions on new fresh test data, then it will happen that the noise, of course, is different, and so having learned the noise in the training data will going to spoil the predictive performance of your model. And the second issue is model interpretability, because it is true that a linear model by itself is quite easy to interpret, but if you have many parameters, this could be not that easy. So it could be difficult if you have tens or hundreds of parameters to understand the role of each of these parameters, especially if the predictors are correlated with each other. And if you have some technique that removes the irrelevant features, so a technique that sets some of the coefficients, possibly many of them, to zero, then you will you will have a few coefficients that are different from zero, and the model will be more easily interpreted. And this has to do with a task that is also called feature selection. So some of the methods that will be introduced in this chapter will help you performing a kind of automatic feature selection. So selecting what predictors are actually useful to have the best predictive performance in your linear model. In order to achieve our goals, we will explore three classes of methods. So a first class that we will start investigating today is subset selection. So the idea is to identify a subset of the p-predictors that we believe are related to the response. Once we have selected the subset, then we can fit a model using least squares on this reduced set of variables. So it's a kind of simplification. So I just throw away predictors that are not relevant to my predictive task. The second approach is quite different and goes under the name of shrinkage. And the idea is that I'm not going to discard from the start predictors, but I will have an estimation technique that, differently from ordinary least squares, has the property of shrinking the parameters towards zero with respect to the usual least squares estimate. This shrinkage that goes under the name of regularization has some nice effects. On one side, it reduces the estimates of the estimated parameters, and this is good, but also it can perform also a kind of variable selection. So it can reduce the number of parameters, especially some techniques like the lasso. There is a third approach, which is dimension reduction. In this case, we project the p-predictors into an m-dimensional subspace where capital M is less than the number of predictors. So the idea is that I compute linear combinations of projections of the variables, and I use them as new predictors. So it might happen that I have 2 or 3 predictors that are combined together, and I use this combination with the coefficients as a predictor in my model. So instead of having 3 coefficients, I will have just 1. So these are the 3 main methods that we will investigate in order to make linear models more effective. So let's start with subset selection. The basic starting method, although we will see it is not the preferred answer, is best subset selection. So let's introduce best subset selection, which is quite natural as a procedure, but we will see that there are some drawbacks, and we will have to understand what these drawbacks are in order to propose better alternatives. But let's start with the best subset selection. So we start with with the initial model that we call M0, the null model, which contains no predictor. So this model just predicts the sample mean for each observation. So in some sense it corresponds just to the intercept, beta 0. Then we start an iterative procedure, and so we have a cycle for k from 1 to p, and at each step, imagine that we have k equal to 1 at the first step, we fit all the models that contain exactly k predictors. So in the first step, I'm going to fit all the models with 1 predictors. These models are models that have 2 parameters, because you have the intercept, which was already in the null model, and then you are trying one at a time all the p predictors. So I will have a model with the intercept at the first predictor, x1, another model with an intercept and the second predictor, x2, and so on. So I have p over 1, which is equal to p, you can remember. I have p models that I am fitting. Now we are at k equal to 1 in our cycle. At this point, I have p models and I have to take a decision, and I have to select the best of these models that I will call mk. How can I select? Well, all these models have the same number of parameters. When k equal to 1, all of these models have 2 parameters, beta 0 and another coefficient. Therefore, it is completely sensible to compare the residual sum of squares, or equivalently the value of r squared. So amongst all these models, I just take the one with the smallest RSS. At this point, I have a model with 2 parameters, beta 0, and then a parameter associated to the predictor that has been included in the model. Then I go to the next step, that is k equal to 2, and then I consider all the models, they will be p over 2 now, that contain exactly 3 predictors. So I am going to consider all the possible combinations. So I will have the intercept, which is already there, and then the intercept and the first and the second predictor, the intercept and the first and the third predictor, the intercept and the first and the fourth predictor, but we also will have the second and the third predictor. So all the possible pairs of predictors plus the intercept. You fit all these models and you select again the one with the smallest RSS, and this model will be called M2, and then I go to k equal to 3, and so I consider all the possible models that include 4 predictors, the intercept, and then all the possible triplets of predictors. Okay, and again I will have M4, which is the best of these models in term of RSS. Okay, at this point, at the end of the procedure, I will have models M0, the null model, M1, the best model with one predictor, M2, the best model with 2 predictors, MP, the best model with P predictors. Okay, and I make the final decision. I just select the best one. Now here you must be careful, because in these steps, you are comparing models that have the same number of parameters. So it's perfectly okay to select the one with the smallest RSS. But in the final selection step, you are comparing models that have different numbers of predictors. So M0 has no predictor at all, just the intercept. M1 has 1 predictor, M2 has 2 predictors, and P has P predictors. And therefore, it is no more adequate to take RSS as a criterion, because the model with more predictors is going to have the smallest RSS among all the possible models. And therefore, you can use some other criteria that we are going to introduce and discuss that are called CP. This is also known as Mallows CP, AIC, Archaic Information Criterion, BIC, Bayesian Information Criterion, or the adjusted R-squared. And these are criterion that in some way penalize the complexity of the model. So they don't just look at the sum of squared residual to the RSS to residuals sum of squares, but they also look at the number of parameters. And so there is a trade-off between fit to the data, which is measured by RSS, and the number of parameters in the model. In such a way, it doesn't happen that you always choose the most complex model. So this is a procedure which is very clear. So the idea is to consider models of different complexity. So you start from the model with just one coefficient, the intercept. So you cannot imagine something less complex than this, and then you increase complexity, you consider all the possible models, you make comparison amongst models with the same number of parameters, and you take the best ones, and finally you have a last selection step where you take the best model. So this is called best subset selection. As a matter of fact, it seems really smart. So you are considering all the alternatives and you are just picking up the best one. Okay, let's see how it works in practice. So we consider the credit data set as an example, and in this case we have 10 predictors. Okay, and you can see that the number of predictors here goes from 1 to 11. Why 11? Because one of the variables is categorical, and therefore you need 2 dummy variables. Okay, so and besides being categorical, the variable has 3 values. Therefore, it is a categorical variable that takes 3 values. As such, you need 2 dummy variables, and therefore one categorical variable with 3 values is going to generate 2 predictors that are the dummy variables. So we start with 10 predictors, but we have 11 coefficients. Okay, and here you can see the RSS for all the models. So here are all the models with one predictor, and since the predictors are 11, these are 11 models, some of them perform very similar, so you can see that many points are almost overlapping. These are the performances of all the models with 2 predictors, and so on. And we are interested in the best models in terms of RSS. So amongst all the models with one predictor, I take the one with the smallest RSS, and which is this one. Amongst all the models with 2 predictors, I take the one with the smallest RSS, that is this one. Here I'm connecting the best models, and so this means that I'm discarding all of these models, and I take only the models whose performances are on the red line. And you can look at the RSS, or alternatively, you can look to R squared, and remember that R squared is better when it is closer to 1. So here, when the model predicts better the data, you have that you are decreasing the residual sum of squares. Here, when the model predicts better the data, you can see that the R square is increasing. All right. So this is how it works. So you consider all the possible models, you measure the performances, you take for each number of parameters the best model, and so these are the 11 models that you are comparing in the last selection step. Of course, you have also the null model, so as a matter of fact, there will be 12 models. Okay. This can be extended also to other models. We are discussing least squares regression, but you could apply the same idea to classification problems, for instance, using logistic regression. In that case, you need something that replaces RSS or R squared, and the index that can replace R squared or the residual sum of squares, RSS, is the deviance, which is defined as minus 2 times the maximized log likelihood. So when you are estimating, when you estimate the logistic regression parameters, we have seen that you are performing a likelihood maximization. Then you take the maximum of the likelihood that you have found, and you have minus 2 times this maximized log likelihood. This takes the name of deviance, and you can compare this in order to select the best model for each class, M1, M2, M3, and so on. So this plays the role of RSS. Okay, and can be used also for other models, not only for logistic regression. Okay, so is this okay? Best subset selection seems very natural. However, it is not the solution we are looking for. For computational reason, first of all, you cannot apply it if P is very large. Why not? Because the number of models that you have to fit grows very fast, and so this can become computationally unfeasible, first of all. But it is not just an issue of computational burden. Okay, there are also statistical problems. Okay, so let's imagine a case when P is large, but nevertheless you are able to estimate all the possible models. This means that you have a very large search space, and then there is a significant probability if the search space is very large. So if you have a really huge choice of models, there is some significant probability that by pure chance you're going to find a model that works well on your training data, but is not going to have good predictive capabilities on fresh testing data. Okay, so it's a kind of overfitting in some sense. So you are considering so many models that by pure chance you find a model that adapts to the noise in the data. So a huge search space has the potential to lead to overfitting, and overfitting is also associated with high variance of the coefficient estimates. And thus also if you use penalized criteria like CP, BIC, AIC in the last selection step. So if we put together these two reasons, the computational problem, okay, and you can see that the number of models that you have to consider is 2 to the p, to the pth power, okay. So both for computational reasons, but also for statistical reasons, that is the risk of having overfitting, this is not the solution we are looking for, and as an alternative, so-called stepwise methods are attractive. And now we will introduce these stepwise methods whose characteristics is that they explore a more restricted set of models. So the danger, the risk of overfitting is reduced, and for this reason they could be an attractive alternative to best subset selection. The first stepwise method we consider is called forward stepwise selection, and the idea behind this method is that you are not going to consider and estimate all possible models, but you perform a stepwise procedure. So you start with the null model, but then when you consider all the models with just one parameter, you select the best model amongst these ones, and then that parameter is kept fixed. So in the next step, when you are considering models with two parameters, you will not remove the parameter, the predictor you have already included, but just you consider the possible inclusion of a second predictor, considering of course only the ones that have not been selected so far. So this is a stepwise, one at a time increase of the model complexity. So I start with the null model, I just include one parameter. At that point, I keep that parameter, okay? And the next step is amongst the p minus 1 parameters that have not been selected, what is the best to be included? I just perform another step, and then I will have a model with the intercept and two parameters. And the next step will be to include a third parameter. And the criterion for inclusion is to select the parameter that gives you the greatest additional improvement with respect to the current model. So in this case, differently from the optimal subset selection, you have a current model, and your idea is that the current model can only be enlarged. So the current model includes some predictors, and your task is finding the next predictor that deserves to be added, to be included in the model. In such a way, it can be seen that you are not exploring all the possible models, because once the first predictor has been included in the model, you are not going to remove it, and therefore you are not going to explore all the models where that predictor is not present. And this is an advantage in the sense that I'm not considering a huge space of potential models, which is the reason for possible overfitting. And on the side, this is an advantage, but of course, there is also the question that our procedure is no more optimal. So it might well be that there is some model that performs better than the models I will find during the procedures, and these models will never be explored because in my incremental procedures I am following a path that never comes close to that optimal model. But let's see in detail how forward stepwise selection works. So again, we start from the null model with no predictors, and then we have this cycle where k goes from 0 to p minus 1. Let's take k equal to 0, for instance. In this case, I'm going to consider all the p model, p minus 0 equal to p, all the p models that include a new predictor in M0. So here now it's k equal to 0, so I have p possible models that are the intercept and the first predictor, the intercept and the second predictor, the intercept and the third predictor, the intercept and the pth predictor, and I just identify all these models and I choose the best one. How can I choose it? I'm looking at the smallest RSS or highest R squared. So for each of the identified models that are identified by ordinary least squares, I compute the RSS and I just take the one with the best RSS. At this point, there is a predictor that has been included in the model. So I started with M0, now my model is M1, and I go back here and consider all the P minus 1 models that include a further predictor in my model. Recall that now I have the intercept and a predictor, so the point is finding a second predictor to be included in the model. Again, I estimate all the models that include the first predictor, which is kept fixed, and all the candidates. I have P minus 1 models, I compare them in terms of RSS, and I just choose the best one. And I go on until k is equal to P minus 1. At the end, I will have a model M0, M1, M2, MP. And again, I have a final selection step which cannot be done using RSS because the more complex models will be favored, okay, and instead we know they could suffer from overfitting, but rather I use some some criterion that penalize model complexity. So I can use the CP, AIC, BIC, adjusted R-squared, but also I can use cross-validation. I didn't say this before, but you can also use cross-validated prediction error. Okay, and so this is the forward stepwise selection. Some comments, okay. The computational advantage is clear, okay, because you can see that at each step I just considering a number of models which in the worst case, that is at the beginning, is equal to P. So when I move from the null model M0 to M1, the candidate models are just equal to P. At the next step, the candidate models will be equal to P minus 1. So you can see that it is completely affordable. So in general, there will be no problem from the computational point of view, even if P is quite large. Okay. So computational advantage is definite. However, you are not guaranteed, as I said before, to find the best possible model out of all the 2 to the pth power models that use subsets of the p predictors. Why not? I've already said the reason. In this kind of stepwise procedure, you have a kind of path. So at each step, you are just considering all possible models that differ from the current model by the addition of one single predictor. So I'm not going to see what would happen if I could remove some of the predictors in the current model, or what could happen if I could include 2 new predictors at a time. I just proceed 1 predictor at a time. So I have a kind of path, and this path is not going to explore all the space of potential models, but it just explores a path, and along this path I am testing, I'm comparing in terms of RSS the models that are at distance 1 from the current model. So the current model plus 1 further predictor. For this reason, there is no guarantee that we will find the best possible model, but overall, I can be rather satisfied. Another issue is whether it is really necessary to go on until you arrive at MP. For instance, if you have 100 or 1000 predictors, is it really necessary to obtain all the models M0 to MP? Usually the idea is that you could stop before arriving at M100, so we'll stop at M10, M20 or something like that. Okay, let's go back to the credit card example, to the credit data example. Okay, so we are comparing now best subset with forward stepwise regression, and here we have the number of predictors that we are using. So for the best subset, when you use one predictor, the best model is the one including rating. When you have using two predictors, the best subset is the one including rating and income. With 3, rating, income, student. With 4, cards, income, student, and limit. So when you have 4 predictors. Then we perform forward stepwise regression. And here we see that in the first 3 steps, the models M1, M2, M3 coincide with those found by best subset selection. But at the next step, when you have M4, you can see that M4 with the best subset is not the same as M4 for forward stepwise, because here we have rating, income, and student, and we must have these 3 predictors, because since this is an incremental procedure, you must keep these 3 and just consider what is the next predictor to be added. In this case, instead, you can see that rating disappears. So rating is within M3, but when you come at M4, you do not have rating anymore in the predictors, and this is something that best subset can do, because best subset is exploring all potential models, and actually it turns out that this combination of parameters is going to perform better than this one. But since I'm using a stepwise procedure, I will never consider this one, because if I have chosen these 3 predictors as M3, the candidates to enter M4 do not include the model with these 4 predictors. And this kind of difference between the 2 procedures is quite likely to occur when there is correlation between the predictors. If the predictors were not correlated, you would see that, as a matter of fact, the 2 procedures are going to give you essentially the same results. Okay, it is interesting to say that there is not only forward selection, but there is also backward stepwise selection, and it has more or less similar features, but instead of having a stepwise increasing procedure, you go backwards. This means that you start with what we would call the full model, the full least squares model that includes all the predictors you have, and then you are removing one predictor at a time in order to see if you can have, in order to find simpler models. And of course, the question is, what is the predictor that I'm going to remove? And the idea is that I will remove the least useful one. But let's see how it works. So here are the details. So in this case, we start from MP, which denotes the full model, which contains all P predictors. And then I have a cycle. For k equal to p, for instance, we start here, I consider all p models that contain all but one of the predictors. So in this case, I do not have candidates for inclusion, but I have candidates for exclusion. So candidates to be discarded. And since the full model has p predictors, I have p candidates. Okay. And the idea is that I will remove these candidate predictors one at a time. I will estimate the resulting model that includes p minus 1 predictors, and amongst these p models, I will choose the one that has the smallest RSS. Of course, since I've been removing a predictor, the RSS is going to increase with respect to the full model, but there will be one choice that will produce the smallest increase of RSS. Okay, and I make this choice. I have a new model which is called MP-1 because now the number of predictors is P-1. One predictor has been discarded, and I go on for the next step. So then k equal to P-1. Now I have P-1 candidate predictors to be discarded. I discard them one at a time. I estimate by least squares the corresponding model, compare them in terms of RSS, and choose the models that gives the smallest increase of RSS. And in this way, I decide what is the second predictor to be discarded. Okay, I go on until I arrive at M0. Okay, and at this point I have again the final selection step, so I consider all the models from M0 to MP and I choose the best one according to the usual criteria that take into account the complexity of the models so as to avoid overfitting problems. Comments on backward stepwise selection. Like forward stepwise selection, the space that is explored is much smaller than the space explored by best subset selection. You can check quite easily that the number of models to be estimated is equal to 1 plus p times p plus 1 over 2. And so you can use this even when p is very large. Even when p is too large to apply best subset selection, you can apply both forward or backward selection without any trouble. Of course, you do not have the guarantee to find the best model, but, well, not a big issue. And however, there is a difference with respect to forward selection because in this case, you must be able to estimate the full model. And if the number of samples n is not at least equal to the number of predictors equal to p plus 1, because you have also to estimate the intercept so that the full model can be fitted. Okay, unless this happens, you cannot estimate the full model because you have too many unknowns. The full model has p plus 1 unknowns, the intercept and the p coefficients for the p predictor. So you need at least n equal p plus 1. In contrast, forward stepwise regression can be used even when the number of data is less than the number of predictors. So this is a difference that you should keep in mind. Okay, an issue that is open is the criterion for choosing the optimal model. We have seen that we cannot use RSS to compare models of different complexity because in this case the model that contains all the predictors, so the full model, will always have the smallest RSS and it will be the winner in all cases. Instead, we are not concerned with finding a model that fits perfectly the training data. We want a model that is going to have a low test error. So it is the prediction capability on new test data that we are concerned with. Therefore, we should not use RSS and R squared, and we need different criteria, but this will be the topic of the next lecture.